Oh, great. Yes, there was some problem with the screen, but I guess that got fixed. Hi, I'm Mariko. So I have like a really weird title on my slide, and you'll get to what this means later. But before that, that's my Twitter handle, and then also GitHub handle. If you are Twitter friends with me, please come say hi. I can't really like match the face and the icon. So like I've been seeing a lot of people who I know from internet. So please come say hi. And if we've never met, please befriend. I work at small company in New York called Scripto as a JavaScript developer. And also I co-organize Brooklyn.js, which is a meetup about world's most famous language in New York's most popular borough. I think that was the tagline. So if you are ever in New York on Thursday, please come say hi. So this talk is a little bit personal. I'm sorry from the beginning, get really personal. So I've been saying it's really hard a lot last year. You know, I got a new job and my scope of the job changed into product developer from like business intelligence developer, and like I started doing a lot of projects, and you know, those like side projects, it's supposed to be fun and I'm doing it because it's something that gives me joy, but I see myself a lot sitting in front of a computer saying like, it's really hard. So like some of the project that was really hard is like making a software for 80s knitting machine and creating a JavaScript scarf. This one was the most tweeted one, but the one that's like interesting to me is one time Travis CI had an API outage, and a ops person tweeted saying like, oh man, like I want to have this graph of like how quickly I came back as a scarf. And at the time, I gave a talk in Berlin. Travis's office is in Berlin, and one of my friends tweeted at me saying like, hey, you should ask Mariko because she can totally do it, and I made it. So I mean, you know, it's also useful, I guess. The another one is I made a small programming language to design textile so that a person who doesn't know any code can code textile design much like they are leading a knitting textile instructions. I also made a punch card, 8-bit punch card computer or leader. So here you see it, there's a paper card goes in and pins are pushed, and right now in this installation it's making a textile design, but I also have a leader for ASCII, so you can communicate letter too. And then like I make silly things like ugly sweater generators. So these, even though like looking back, I think I'm maybe proud of those, like some of the things that I did, but then it's also a reminder of like how miserable I was when I was doing project. So like, you know, I thought of it as like, I was at this, like, I've been programming for maybe 5 years and professionally for 2.5. And I analyzed myself. Previously I was a product manager, so I'm like really into like thinking a process and like what can improve. And I was thinking like, I'm at the point of programming experience that gluing code and learning new library was no longer fun. It felt like magic when I first animated a button with jQuery, but the same thing became just the source of my insecurity of like, I don't know what's going on. I can talk to this library and I know this API, but I can't really understand what's happening, and you know, I feel like I'm just gluing a code of like somebody wrote. So at the end, even though there is a tough time, I release the project on Twitter, and you know, the likes and retweets come roll in, and I feel like, again, like, oh, maybe I learned something. So I looked at, so writing this talk, I kind of like looked back the project that I did and why it was so hard, and I realized that like, I didn't know magic is made out of many dumb steps. And I thought the magical thing that people were doing is achieved by like a genius programmer. But actually, I didn't know that those are actually made out of many, many dumb steps. And I put asterisk on dumb. I don't mean to be rude to computer. I'm just deliberately using word dumb as opposed to smart. We, as a programmer, like to say smart things like smartphone, smart car, smart everything, smart house, smart IoT, I don't know. So it feels like something that genius and many, many hours of programming achieve that smart and magical thing, but it's actually very small, dumb steps. So once I realized that, I started taking notes and started drawing a lot. This is a first paragraph of Last language. If you go to their website, like a first introduction to what Last is. And the borderline as red is things that I don't understand. And the notes are things I researched and I learned about those, like a little simple thing that constructs this Last programming language. And I started feeling good about myself by just deconstructing something that felt like magical and something that felt like over my head and started understanding. So today, I want to show you one of the magical things that I thought it was like kind of amazing, and turns out it was kind of simple, and roll back how simple it is. So, let's see. I have a little demo made. So, if you know a augmented reality, like Pokemon Go is an augmented reality game, although Pokemon Go is a non-marker game. So they use location information to show the information on your screen, and there's a marker-based augmented reality. Much like QR code, you read it on the phone, and they return you the data. Or if you use Snapchat, Snapcode is the good example that they give you some kind of image, and once you take a picture of the Snapcode and upload it, they will tell you which user that Snapcode is. So I made a little demo of once you have a JS logo, and this slide is a little finicky, so it might be a little flickery, but once you put the JS logo over it and then computer sees that it is a JavaScript logo, I can display the information about JavaScript logo designed by Chris Williams and showing information. So I was wondering why augmented reality markers are so ugly. They're usually just a box of black and white pixels and never actual visual that you want to use. And I wanted to know if I can use regular image as a marker. So, I need to close this, otherwise my computer is going to be dead. I chose augmented reality and imaging because a lot of my side project involved dealing with images. As I mentioned, I knit with code, and the process, 80% of that process is taking a digital picture and thinking about the way to translate that into yarn. Yarn doesn't come in hex colors. You can only use 2 to 4 yarns. So you need to apply a lot of image processing to get it right, get it look like a picture, but it's actually represented in limited color. So I started researching, and there's a lot of math and a lot of white papers, and I usually end up researching a website from a university. And also people ask me, why don't you just do it in Photoshop? But I just don't know how to use Photoshop. And I challenged myself, can I do it in the environment that I'm most familiar with, which is HTML and JavaScript. So without further ado, let's just roll back how that AL tag can be made for browser or with JavaScript. I use an element called Canvas. It's a HTML5 element that can be used to draw graphics using JavaScript. So it's perfect for this project. I can write code that is my most familiar with. I don't have to learn C, and I can just use the browser as my medium. So, starting a canvas, you can just create an element, or you can type it in the canvas tag and just refer to ID, and you create where you set the width and height. And I call this step buying a piece of land, but you still don't know which neighborhood that you're buying, but you know the size of the piece of land. And then you need to set something called context. And context is something like defining a neighborhood. So if you set the context for WebGL, you might have a piece of land in very like 3D GPU like particle kind of thing, or you can set context in 2D, which is very flat and 2D images. What context gives you, much like a different neighborhood has different language and different dialect, the way to communicate to this piece of land, it's still JavaScript, but they have like a specific language that they use. So rest of the demo is going to be in 2D context. So in 2D context, you have language like .lect, which lets you put a rectangle on your canvas or draw an image, which you can draw, basically import the image into canvas. And once you draw something on the canvas, you can call something called getImageData and just extract all of the data out of that canvas, or use putImageData to add whatever the data you want to in the canvas. So this is a little wrap up of like what this process is before we go into this cool things part. You have an image, you create a canvas, you set the size, and then you set a context. Then you get the image data, do some image processing, create a new image data, and put it back. And from now on, we're going to talk about what happens in this pink area. So let's talk about this image data. What does that look like? Well, image data looks like this. And looks like it is not. There you go. So image data looks like this. So imagine you have very tiny image, like 3 by 3 pixels, just enlarged on the screen. Image data is a JSON object that contains all the information about this image. So some attributes like width and height are straightforward, numbers of width and height in pixels, and they have a thing called data. And data is this series of numbers that I didn't know what that is at first. So let's read what the data is. So in order to understand data, you need to understand what constitutes a pixel. A pixel underneath contains 4 data, and 3 of which are light bulbs, red, green, and blue, illuminating in different level, depending on what kind of color. So if I want to make this pixel red, then I fully illuminate the red channel, and then turn down the green and blue, and you get that red pixel. If you have a same number for 3 light bulbs, then you always get gray, and this is how you grayscale an image. 4th number, at least in the canvas pixel case, there is opacity. So it is basically how to blend 2 colors if 2 color are overlaid together. And if you write a CSS colors in RGBA, this is just a same thing. Right. So I can just look at this picture like this. I added like eyes and padded the data. So once you have it, each pixel has 4 numbers. So the first 4 numbers are 4 top left corner pixels, and then next 4 numbers are a second from the left top pixel. So I can do the same thing I did in interactive demo. Like I max out the red value and turn off all of the green and blue value, and I can update it to have red. So this is how you manipulate an image and add something like Instagram filter or changing the color of things. This is what's going to happen. So to wrap our head around this, because data is one-dimensional array, I think of it as like writing a letter. When you're writing a letter, in your head, text are in one-dimensional stream of text. You don't think about, oh, I have to put rhyme break here, or I have to add a few letters to make it into like a light spacing. But if you're writing a letter on paper, you just naturally, as soon as you run out of space, you line break and then put the data into it. So pixels are like that. The data itself is a one-dimensional stream, but then when you project it onto the 2D area, then it's just padded. So that means you see a lot of these code basically going through the pixel numbers to see which position this color, 4 sets of numbers are for by XY position. So it's double nested for loop, an outer loop goes through the rows, and the inner loop goes through the column, and you get a position of pixels. So once you have that, you can make like something fun called like, one thing I made is something called ghost image. You upload an image, and I give you a CSS file and a div tag. And what it is 1 by 1 pixel, but I add you like a whole bunch of box shadow to represent the image. So this one here is actually 1 by 1 pixel div, but it kind of looks like image on CSS. I haven't found the usefulness of this thing, but it was fun. It was fun. So I said that if you change the color, you can apply Instagram filter. So a little quick. So if I take the input of 196, and if I output 196, then color doesn't change. So you just get a photo that you included. However, let's say like inverted filter. That means that you have input of high input, but then the output is always low, and that creates an inverted effect. Something like posterize is a way to limit the color. So in this case, from 171 to 155, if you input that range, then it always comes out as 255, and you can posterize that image and kind of like create a fun effect. I have a whole bunch of examples, and I wrote a library to teach people how these works. This is no way performant or the best way to do it, but at least the code is very simple, and you can kind of follow along what happens. So if you're interested, check that out. But I'm going to move on to different parts to do that augmented reality marker. So in order to achieve this marker thing, you need to know 2 techniques of image processing, which is grayscale and thresholding. And it's basically asking pixels, how bright are you? So let's say you have original image, and as I told you on the color demo, if you have a same number for each 3 channels, then you always get gray. So the original color of each object maybe look like this, and you just need to decide one number to represent this color. So let's take like very naive approach of like choosing one channel. So green, like the middle number, just repeat it over red and blue channel and create a gray. And that running into problem because white, the green channel for white is 255. A green channel for green is also 255, and you're just like not taking account of other colors effect. So let's say, well, how about if I average it? And you get average of 3 channels like this. And this is getting to look like a grayscaled image, but one problem is that these 2 boxes, it's 00255 and 02550. So as a number, it's the same average number output. However, as humans, eyes are very biased to green. So when you look at the original image, green feels like a lot brighter than the one on blue. But in the computer's mind, it's the same thing. So we need to take account of how we perceive the color. And there is a variety of ways to calculate this and variety of codec to do this, but I use a Luma coding, which is used for TV, to basically give advantage to a little bit to the green channel and red channel to mix it so that the output grayscale looks like how we perceive this image. So once you have that grayscale, you can apply another filter called threshold to extract whatever you need. So what threshold does is much like posterize, that if this pixel is from 127 to 255, then it's just turned all the way out as a white pixel. And if it's lower than that, just give a black pixel. And then this will get you complete black and white image. So if I want to extract only that symbol, then I adjust the level. And if I want to extract two to add more, then I just play around with the level to extract what's interesting to you. So with just these two filter knowledge, you can kind of make interesting thing. Here's the artwork from 2007, and it is called Laser Tag from Graffiti Research Lab. And what they're making is the audience gets a laser beam, and they just draw a line on the building, and they just make a graffiti graphics projected onto that building as kind of projection mapping. And I actually studied communication and studied new media as a minor. So when this came out in 2007, it felt like much magic was happening. Some kind of very highly sophisticated motion tracking was happening. And this project sounds like very costly. But in fact, I found out later that this was only tracking the brightest pixel in that region. So the camera is actually looking at this building area, and because it is laser is going to be always brightest pixel. So that's how, as the video feed comes in, they process where is the brightest pixel, and they follow that line to draw the graphics. And I thought that was kind of clever, and also kind of disappointed that was that simple. But that's what I mean, the sophisticated looking things are very dumb steps. So let's move on to labeling and edging, and this is the last thing that you need to know to create an AR marker. So labeling and edge detecting is asking computers what's inside of this image. Because we grayscaled it and threshold it, and let's say we have this image, but as a human, we can easily tell what this image is. There's two areas of interest. So there's two objects that we have, and two objects are definitely separated in which location and what kind of shape each of them have. But at this point, a computer only has the information that which one is a black pixel and which one is white pixel. They don't have any relational information. So let's just give them how your neighborhood is drawn. So I call it pixel social graph because it's much fun to think pixel as humans and creating a social world than just applying math functions. So I just humanize it by putting eyes on it. So let's do labeling. Labeling is basically detecting a blob of object and kind of separating a pixel. Oh, you belongs to this neighborhood and you also belongs to this neighborhood. So let's start with the first white pixel. Remember, the pixel data is from top left corner all the way in the linear function. So this would be the first white pixel the computer would encounter. And it just labels as 1. Okay, you're group 1, this was the first one. And next one, computer asks, are you connected to any other pixel that I already labeled? No, so this one gets 2. This one is kind of interesting. It asks the same question of are you connected to, meaning sharing a size and top bottom, with the pixel that you already, which is already labeled. It looks like it belongs to this label 1 from human's eye, but as far as computer is concerned, it's not connected to any of the pixel that's labeled yet, so they just give 3. And next one asks, are you connected? And this time, definitely connected to 1 and 3. So computer is okay, I'm just going to give this pixel the 1 group, but take a note that 3 was also a possibility, so I can come back later. And do that thing for all. And then you have a 3 labeled, so you go back to 3 region and re-evaluate again. And indeed, it is connected to region 1, so you turn those 3 into 1, and voila, you have 2 separate blob as labeled. And now computer at least knows that in this image, I have 2 areas of interest. I have 2 objects that I need. But computers still don't know where the boundary of those images are. They only know where is the black pixel, where is white pixel, and of which white pixel, which one is 2, and which one is 1. But they don't know within 1 which one is on the edge of the black or which one is the inside of that blob. So let's label the edge. So again, start with the first pixel. And it's first pixel, and it's the first encountered white, so it's definitely on the edge. And then they ask question again, this time including corners, saying, is there any other pixel in your group that surrounded you? And looking at left, no, that's not group 1. Looking at the corner, oh yes, it's 1. So they move the boundary to there. And they kind of like step by step go through, try to find the boundary. So ask same question, is it 1? No. Is it 1? No. Oh yes, it's 1, so they draw the line, and you do that all the way, and you now know which pixel is black or white, which pixel is group 1 or 2, and of which group 1, which one is on the edge, and which one is inside. So, believe it or not, as with this information, you can just recreate that arrow marker. You don't need to introduce machine learning. You don't need to learn about C++ library or OpenCV. You can just extract this data and apply it to make augmented reality markers. So you have computer start with reference. So I have a JavaScript logo reference image and define it as this marker looks like this. And it's a rectangle, and it should be more than 100 pixel wide. And that's the starting point. Now you get the data feed from the video, and as I hold it against, you basically have distorted version of that marker. But I apply grayscale filters, and I apply threshold filters, and I do labeling and edge detecting. At this point, with only that information, you can kick out this label 1. Maybe it's smaller than 100 pixels, so let's just kick out. And you're left with 2 regions of interest that could be a marker. So let's define, or let's see if this is marker or not. So let's extract a one graphics. And as we told, there is the beginning pixel, there is always the first pixel that image interact, the first white pixel that came, or in this case, black pixel that came into this data feed. So from that first pixel, I ask a question about what's the furthest pixel from this one, and you get 0.1, and labeled it as a corner. And from 0.1, I ask the same question again, what's the furthest pixel I can find? And that's 0.2. Because if this was not rectangle, then the beginning pixel and 0.2 might be different locations, so you need to do that. You draw the line between P1 and P2. And from this line, you ask the same question, what's the furthest corner from this line? And you find P3 and P4. And at this point, you find like somewhat corners of a rectangle, and this image is turning to be looking like indeed maybe a rectangle, because you draw the line between P1 and P2 and P3 and P4, and those lines cross over. If it is rectangle, then it will always cross over. So this is the part that I have like massive anxiety and massive like imposture of like I don't even understand and why am I speaking at a conference kind of thing. But you apply things called homography to transform those corners so that image that is distorted is now facing straight and it's in the perfect rectangle. And as you can see, that's the math that you get from white papers, and I somehow wrote a code that does it. But it seems to be doing okay. I can do the demo, but I still don't know exactly well, at least I cannot really explain it to you, sorry. But you apply a thing called homography in graphics, and then you get a perfect rectangle. So now the 2 blocks that was distorted before is now in perfect rectangle shape. And you call the reference image and ask them, is it same as the reference image, or is it not? And because we have a pixel by pixel data, you can verify whether an image is exactly the same as the reference image. So that's how I did that demo. So I think I'm over time, so just quickly, if you were interested in making these applications, thinking about performance is important because, as you can see, there's a lot of computation happening to make this interactivity happen. So I use WebWorker to kind of make sure that I don't block users' interaction on the app while I'm doing heavy computation on the background thread. So I think if you were at the Nolan's talk, you basically know this already. But WebWorker is a way to run your JavaScript in background threads. So I consider it like WebWorker is an International Space Station. So you launch the WebWorker, and you can send the data, and you can do any computation, scientific research on the worker side. But because it is an international station, you can't touch the element in Earth, which is DOM. So you don't have access to window, you don't have access to jQuery selectors. You just have a mental separation of like, oh, why can't WebWorker just select the ID? Oh, that's why, because it doesn't have access to the element. So this is how simple using WebWorker is. I'm going to quickly walk through. So you create a worker by new worker and give a script that you're going to run in the worker side, and that's like launching an International Space Station. Inside of the worker, because you don't have access to window, even though you have underscore already loaded on your DOM or something, you still have to, again, import the library. So if you need to, you use import script. And once that's set up, you communicate between DOM and WebWorker by using post message method and on message listener. And this is where you pass the data. And you keep your UI interaction in DOM while expensive calculation happens on the worker. And Nolan told me you don't really have to terminate workers if you know that you need it later. But if you definitely need to kill the WebWorker, then you just call terminate and like consider that as like extending to black hole. So here's a little demo of worker version and non-worker version. I have a heavy computation happening in this. I'm creating a tilt shift image. And the worker side, the animation is still going smoothly, and the thing is applied and finished faster. But non-worker side was totally blocking the thing. So once the finish, it's just the blob of interaction that I clicked on it comes back. And this creates a user frustration of why is my app not working when heavy computation is happening. So using worker is very simple, and you can get started really easily. I highly recommend looking into it. So in conclusion, what did we learn today? We learned that the pixel have a social life. It's much fun to think about pixels in googly eyes. And I hope I made a case that something that looks very majestic and special and maybe like deep learning and deep dream and machine learning and all of that Google Genius stuff is just a series of dumb steps. And I use dumb in affectionate way as opposed to smart. So that's my Twitter handle. I have googly eyes on my badge. If you find me, come talk to me. And if you want googly eyes, I also have a set of them. Thank you very much.
All right, thank you so much.